In this video, we're going to look at electric generators and electric motors, and we're going to try to examine them through two frameworks, both conservation of energy and then through Faraday's law, where we look at the rate of change of magnetic flux. We'll try to understand how this is linked to how we make electricity in our society. Let's start just by thinking about conservation of energy.
But first I want you to take a look at the generator. It basically consists of three things: a wire coming out of it, a crank where we can put work into it, and a coil of wire spinning in a magnetic field. Now when there's nothing hooked up, like right now, I got these loose clips, it's very easy to turn this. In fact, I could push it and it'll take a little while for it to come to rest. But watch what happens when I hook it up to the light bulbs. Now, I really have to push it. And if I give it a push like I did before, it comes to rest pretty quick. And in order to get these light bulbs to light up, I actually have to put a fairly substantial amount of work into it. And what this is demonstrating is essentially conservation of energy. There's power being produced by those light bulbs. That means there's a certain number of joules per second being burned by them. You got to put the same number of joules per second into it in order to produce that. So the more load you put on a generator, the quicker the generator needs to do work. And that's why you buy generators rated in watts. What kind of motor's hooked up to that generator? How much power can it produce?
Let's try to link this conservation of energy idea now to Faraday's law. Just as a reminder, this setup is an air-cooled solenoid hooked up to a galvanometer, and we are going to change the flux by changing how much the bar magnet is inside the coil.
But it's not enough just to have a magnet. Current, but now no current. Current when I move it. The magnet has to be moving. If you can continuously move a magnet, you can continuously make current. So what would that look like? The magnet would have to keep moving up and down, basically. And as you can see, the needle goes back and forth. So this is not a current just in one direction. This current alternates.
Let's look at a related situation where instead of moving the magnet, we move the coil. We'll see if that gives us any insights and whether we see this pattern of alternating current continuing to happen.
I now have another coil. This is a 200 turn coil. It's got a bigger radius than the previous one. And that's it. There's nothing else. What's kind of cool about this setup here is that there is a magnetic field in this coil right now. And that's because the Earth has a magnetic field. North is pointing in that direction. But check out what happens when I pick up this coil and start moving it. The more I move it,
the more the galvanometer seems to react. And we need to come up with an explanation for that. It's important to understand that right now there's magnetic field pretty much perpendicular to this picture everywhere you look. There's magnetic field lines essentially like this, according to the compass. And they exist outside the loop too. What Michael Faraday figured out was that it wasn't the overall magnetic field that was important. It was the magnetic field that was inside the loop and its relationship to the current, which we know is moving perpendicular to that, like maybe in this direction right here. So Faraday had to come up with how the amount of magnetic field, its interaction with the coil of wire, both in terms of how big the coil is and the angle, and how those things can all sort of combine together to create a current. And so to help it make more sense out of this, we're first going to start with a new definition of something called magnetic flux. And it's kind of like magnetic field plus. It's not the total magnetic field, which obviously can exist both inside and outside the coil. It's kind of like the magnetism inside the coil. So what would that depend on? It would depend on the strength of the magnetic field. It would depend on the area enclosed by the coil. If this shrunk or grew, it would enclose more or less magnetic field. And it would depend on the angle. That's a little bit tricky to see. But if we imagine the coil is lined up perfectly with the field such as that, and then we start to rotate it, if this is the head-on view, we're seeing field going all the way through, but now it's almost like the eye is closing and less field can get through. And when we're perpendicular to the field, no field can get through. So we would call this maximum flux, and we call that minimum flux. And what Michael Faraday realized is that it's the speed at which you change flux that causes an EMF, which is kind of like a voltage.
So even the weak Earth magnetic field can produce a measurable EMF and therefore a measurable current when we rotate the loop fast enough to notice. Notice this is an alternating current since it's going back and forth. So I have here a fairly ancient model. I think it might even be older than the school, but it's a really good model of how an electric generator works. It's going to convert the mechanical energy I put into it into electric current. There's a few basic parts to it. There's obviously the crank. There's a magnet.
So this kind of horseshoe-shaped piece right here, that's the magnet with the N and the S on it. Notice it's got wires on it too because it's actually an electromagnet, which makes it much stronger. The most important part of these coils of wire, there's this kind of hockey puck thing here that gets in the way, but this is basically the coil. And since we know the flux lines go out of the north and into the south, right now there's kind of maximum flux going through the coil, or close to maximum. Here's like a top view of that on a slightly different model. This one would actually be at maximum where it's perfectly perpendicular.
When it's like this, the minimum amount can get through because that donut hole's facing away from the magnetic poles. So as I crank this, the flux will increase and decrease, and as we've seen, that generates an electric current. So I'm going to keep cranking always in the same direction. It's alternating. It goes back, forth, but I'm still cranking in the same direction. So what I'm making is an alternating current. And I want to talk about why that is.
So to understand this, we really need Lenz's law. So we saw that we had maximum flux when we were in this situation, which, if we're looking head-on, would look like that. And we have minimum flux in this situation. And there's what the model looks like. 0 Webers because the coil angle means that cosine ends up being 0. So that means that for this half cycle, the flux, which in this case is into the board, is decreasing. So we know through Lenz's law that nature will try to increase flux, and the best way to do that is to put a current in the wire that creates inward flux inside the coil and outward field outside it. We know from the right-hand rule that magnetic field would look like this, and we'll get that if we have a current that's facing down, and therefore I called it clockwise in that case. I guess if it's a clock facing to the left side of the board. In the second half cycle, as we go back to maximum, we have an increasing flux, which in this case is an increasing inward flux. So nature's going to try to fight that, and the only way it can is by creating an outward flux inside the coil and inward field outside. So as you can see, the right-hand rule tells us the current will reverse. And the point to all this is that the natural state of generators is to give alternating current. If we want to get direct current, we have to come up with some tricks to figure out how we can get direct current out of one.
And now I have it set up to give direct current. So I'm going to rotate clockwise like I was before. And I'm not going to change that. But watch it's never going to the right. It's always pulling to the left. It's really different than the back and forth we had before. So this actually is direct current. Although it's pulsing, there's always a positive and there's always a negative.
Alright, so how is this strange pulsing we're seeing on the galvanometer representing DC? For a battery-powered DC circuit, we expect a current versus time graph to look like this. Pretty much constant, maybe a slight decrease as the battery drains. And what that represents on the circuit is current leaving the power supply, going through the circuit and coming back, always in one direction. When we had the generator wired for AC and the galvanometer was flicking from 0 to positive, back to 0, then to negative, then back to 0, then to positive, it was showing us a truly alternating current. That current grows as the needle gets farther away from 0, reaches a peak, and then comes back to 0. But notice in this part of the sine wave, the current's always in the same direction. It's always still in that same positive direction. It's only when we cross the 0 and the needle flicks to the left, this half of the cycle, that the current would reverse and go the other way. So the simplest way to make a DC current would be to literally just hack off half the cycle. Just literally delete the bottom half, disconnect the circuit during the bottom half. This actually is a DC current. It's got an increasing to a max and then decreasing back to 0. It's got a time when it's off. It increases to a max and back to 0 again. But all that time, the current's always heading in the same direction. Now, of course, this is a pretty inefficient way to run our generator. It would be amazing if we could get the second half of the cycle back, but somehow inverted. Let's take a look at how a DC generator can do that.
So that's really different behavior than before, and I want to explain how. It has to do with the configuration of the brushes. So notice they're no longer hooked up here and here like they were before.
We know that in the coils of wire we have an alternating current, but we're going to add in something called a commutator, which is this piece right here, actually both sides of it. And notice that basically it's two pieces of metal that are isolated from each other. One is hooked up to one end of the coil, the other is hooked up to the other end of the coil. And bottom line is, because there's these brushes, one of which is hooked up to the positive side of the galvanometer, and the other is hooked up to the negative side of the galvanometer, we don't end up seeing a reversing alternating current, because what happens is, at the point when the current would want to switch direction, the commutator has rotated and it connects to the other brush. So basically, the natural alternating current that we have in the coil of wire, we switch it to being a direct current by having, every time we rotate the commutator, a different brush is touching. So the two effects cancel each other out and we get that sort of pulsed DC current. We're going to see that for both generators and motors, brushes and a commutator are key.
So again, the generator, you put in work, coil spins, there's motion, makes current. But if you go back and think about how a motor works, it's kind of the opposite. If you put in a current, and the currents in a magnetic field, that causes motion. So that raises the question, are they reversible? And in fact they are. So 2 generators, I'm just going to cross connect their clips. So now they're hooked up, and I'll give this one a crank. And we can see that not only are they similar, they're exactly the opposite. The one in my hand is the generator it was before, but the one on the table is acting as a motor. And there's not like there's any special thing about which one I chose to make the generator and the motor. They both can be. So what's happening here? I have a small electric motor of the type on scitoys.com. It consists of a coil of wire with some special insulation, which we'll talk about in a little while. A magnet, it's in that bundle of masking tape, and a DC current caused by a 9-volt battery, which is here 6 D cells. And as you can see, all of that alone is enough to keep the coil of wire spinning. So I'm going to stop it, and we'll discuss what's going on here. So I disconnected the battery. And as you've learned from the discussion of forces on charged particles, the force on a charged particle moving in a magnetic field is perpendicular to both the field and the motion. So we can tell from the motion of the loops of wire that there must be a force on this bottom rung actually towards the camera and one on this top rung away from the camera, because that's what makes the thing spin. So here's our diagram of that. Got all the essential components we've talked about. We have our magnetic field caused by the magnet in orange, that's B. We have the forces I mentioned, bottom one coming out towards you, the top one going away. And you could see that if you were holding your hand on that coil of wire and pulled them in the direction of those forces, you'd put a torque, you'd cause it to spin. So we'll pretend there's positive charges going through this wire. And it doesn't matter if that positive charge is in the wire versus in the air. It's still cutting across a magnetic field just like I did. So on this loop of wire, the right-hand rule says that charge is going to have an upward force on it. And remember, there's trillions and trillions and trillions of charges doing this, and they all have an upward force on them. That tends to pull this wire up. On the other side of the loop, it's going in the opposite direction. So just like I had opposite force on me when I switched directions, these ones will have opposite forces. So that pushes this wire down. And between that push up on the left and pull down on the right, that causes a torque and it causes the thing to spin. On the parts that are in the same dimension as the magnetic field, so here and here, there's no force, so they don't contribute. So that is what makes the thing start to spin. So there's one final issue with the motor. If the coil is set up at first so that the current is going in a clockwise direction like this, so the right up top and the left on the bottom, it's not going to stay like that. As the bottom comes towards me and the top goes away from me, it's going to flip. This bottom piece will move up and become the top piece, resulting in on top the current will go the other way. That will reverse the force too. And what's going to happen is as the thing rotates, the two situations are just going to go back and forth with the force constantly reversing. Let's see what that looks like. It's definitely a magnetic force. It definitely started going, but it's like it's rocking itself back and forth. First it goes one way, then it goes the other way. It doesn't really lead to any sort of net motion. It's almost like the forces are opposing each other. They pull one way, then they pull the other, then back and forth, and nothing happens.
Alright, so let's try to solve this problem, and we're going to do it in a way that looks a lot like the brush solution from before, where we control when current gets to certain parts of the rotating loop.
If we spin the motor, you can see that half of the enamel's been rubbed away, but the other half is still there. And that means that when the motor's like this, the copper wires are touching and electricity's flowing. But it's when it's like this, the supports are touching the paint and electricity's not flowing. So in this state, it's actually turned off. But when I flip it over, it turns on. So our motor's only on for half the time. When I give the loop of wire a little kick, it keeps going. And it's actually acting as a tiny little electric motor. The chemical energy of the battery is being converted into kinetic energy. So we can see it works if we just eliminate one of these two situations. If we just turn the motor off when it would be like this. And then it gets its push when the current is clockwise. It then switches off and coasts through the other half of its cycle and then gets a push every half cycle. It's not the most powerful way to build a motor. A much better way would be if we could switch the direction of current as the thing rotated. Let's look at a motor that can do that. So I have another motor here, and this is called a St. Louis motor, and it's a really good model for all practical DC motors. So this is a model for how the fan in your laptop works, or how a motor in a remote control car, or really any battery-powered motor does its job. I'm going to stop it from spinning, and we'll take a look at what the pieces are. So in the simpler motor you saw, the one from SciToys, we solved this problem by just having the motor be off half the time. The rotating part only made contact with its power supply 50% of the time because I only scratched off the insulation on half the wire. This has a much more ingenious solution. I don't know if you can see it, but that piece of metal is broken in the middle. It's broken on the other side too. And these things that are touching the spinning part, these brushes, they're what are actually hooked up to the power. And they alternately touch one side of this metal spinning jacket or the other. And what that means is it's constantly switching back and forth, whether positive or negative is touching each side of the jacket. And that means the coil is reversing the direction of its current, just as if it was alternating current. And that means that we're always getting pushed in the right direction because the time after we've gone around once, it flips, current reverses, so now it continues to push in the direction we want. So it's on all the time instead of half the time, like the previous motor. With an AC motor, you don't have to because the current automatically reverses, so an AC motor is much simpler. But there's lots of applications where we need a battery, which is portable, to power an electric motor, and this is how it works.
All right, I hope you enjoyed the video. Just a quick summary of the key points. When you create an electrical current by rotating a coil of wire, you create an alternating electrical current. And that's the native current that generators make. We can get direct current generators by introducing the idea of commutators and brushes to switch the direction of current for us as we rotate. And we should also understand that motors and generators have symmetry to them. If you put in the work and it makes electricity, it's a generator. If you put in the electricity to get work out of it, it's a motor. Thanks for watching.